Hey everyone, in this video I'm going to be solving the following integral here using trig substitution. As with my u-substitution video, the reason I'm solving this integral is because I need it for one of my other videos on aligning torque. So the first question is, can we solve this integral using the simpler u-substitution that we used in the other video? And this integral actually looks simpler than that other integral. And so let's try to do that. Let's say that we're going to substitute in u for this term again. So we say that u is equal to 1 minus x squared. And as we did before in the u-substitution video, we take the derivative of this to get du is equal to negative 2x dx, because we're trying to get rid of all the x terms and change them into u terms. And so if we solve for dx, because that's the only other term that's still not a u term because this is equal to u here, then we get dx is equal to negative 1 over 2x du, and if we plug the u in for here, and then we plug this expression in for dx here, we can rearrange this integral like this, but you can see that there's still an x in the integral, so it's a mix of x and u's, and so the answer is no, we can't use u substitution for this. We're going to need another method, and that other method is trig substitution. So the method of trig substitution is similar to the u substitution in the sense that we're going to transform from the x variable in here to some other variable theta. We're going to integrate it, and then we're going to transform back from theta to x. Now the way that we do this is a little bit different, so I'm going to define this triangle, this right triangle here, with side hypotenuse a, and then this side is x, and this side's y with an angle theta here. And we can solve for what this side y is in terms of x and a, where x is this variable up here. So we can just use Pythagorean theorem and say that y squared plus x squared is equal to a squared. We'll move the x squared to the other side, so we get this, and we'll take the square root of both sides, so we get y is equal to the square root of a squared minus x squared, and we can put that in here, so we have a squared minus x squared, square root of that. And now if we say that the hypotenuse a is equal to 1, we can just rewrite that like this, and so we have the hypotenuse a is equal to 1, this is still x, this is still theta, and we plug in 1 here, and 1 squared is 1, so we get this side here is equal to radical 1 minus x squared, and you can see that this term right here looks like this term in our integral. So now we can find expressions for x such that we can plug in for theta into this integral. So the first thing I'll do from this triangle is take the cosine of theta, and the cosine of theta is the adjacent over the hypotenuse, which gives us just radical 1 minus x squared. Then I'll take the sine of theta, which is the opposite over hypotenuse, which just gives us x over 1, which is just x. And then note that we'll also need a dx, so I'll take the derivative of this expression here, and so I get dx is equal to the derivative of sine theta, which is cosine theta d theta. And so we can plug in for this integral up here, because you can see that we have this term, the radical 1 minus x squared, and that's just cosine theta, so that's this first cosine theta. And then we also have for the dx, we have cosine theta d theta, that's where this cosine theta d theta comes, and then we can get the multiplication of the two cosines, and that gives us the integral of cosine squared theta d theta. Note that we could also have reached this conclusion here by not worrying about doing the cosine theta term and just using the sine theta term, so you can see that we could plug in for x, we could plug in sine theta, so we get radical 1 minus sine squared theta, and then still we have this dx is cosine theta d theta, and we'll note from the trig identity that sine squared theta plus cosine squared theta equals 1. We can rearrange that to this and plug in cosine squared theta for this term under the radical, which gives us a radical cosine squared theta times whatever we have here, and a square root of that will just give us cosine theta times d theta, and then we'll end up at the same result that we did before. So at this point we're trying to solve this integral here, the integral of cosine squared theta d theta, and note that you can just look this up in an integral table at the back of a book, but we're going to go through the actual solution here. So we're going to use a power reducing identity here for the cosine squared term, which is 1 plus cosine 2 theta all over 2, and so we plug that into the integral, and we still have the d theta term, and we can split this up into two separate integrals, the 1/2 d theta, that's the first one, and then the cosine 2 theta over 2 d theta, that's this second term here, and we can easily integrate both of these terms. So the first one we integrate, and you can note that you can take out the 1/2 from the integral because it's a constant. We get 1/2 theta, and for the second integral we get 1/2 sine 2 theta over 2. This over 2 takes into account the fact that we have the 2 theta in the parentheses here, and then we can simplify this down to get theta over 2 plus sine 2 theta over 4. I've just taken that result from the previous whiteboard and put it up here, and we need to get rid of this sine 2 theta or change it into something that's more useful. So we'll use the double angle identity here for sine 2 theta, which is equal to 2 times sine theta cosine theta. You can note that it takes the 2 theta and brings it down into single thetas in these trig terms. And so if we just plug that in for sine 2 theta up here, we get this up here, and so we still have the theta over 2, stays the same. The 2 and the 4 gives you a 1/2 times the numerator, the sine theta cosine theta. And now this is the result of that integral. Again, we don't have that plus a constant because I don't need that for my future video, but usually you'll have a plus a constant for an indefinite integral. And so now we're going to convert back from these thetas to x to get our final solution. And so you'll note that we need an expression for theta in terms of x, sine theta in terms of x, and cosine theta in terms of x. And that's why I've left up the triangle again, because now we have expression for sine theta, which is just equal to x over 1, which is just x. The cosine theta is the same as before, which is 1 minus x, the square root of 1 minus x squared over 1, which is this. And then theta we can just solve for by taking the inverse of the sine of x from this expression right here. And if we plug all those back up into this expression up here, we get the final result for the integral for this integral is equal to inverse sine of x over 2 plus 1/2 x times the square root of 1 minus x squared. Thanks for watching.